this section, we're going to be looking at moments, centers of mass, and centroids. And these are all things that we can sometimes use integrals to calculate. Okay, just to get started, I want to go over a couple of basic things from physics. We have a tendency to equate weight and mass because so often when we're working with a problem that involves either one of them, we are assuming that we're on the surface of the earth, and so weight and mass can be a little bit interchangeable. But mass is actually the amount of stuff that's in something, and if I take that thing and move it from the earth to the moon or from the earth to Jupiter, the weight of it is going to be different because the weight involves gravity as well. So we want to make sure that we don't equate force and mass. Gravity is a force. Weight is a force. And our basic equation is force is equal to mass times acceleration. Okay. In the U.S. system, our measure of mass is the slug, and our measure of force is the pound, which can be expressed as slug, the mass, times the acceleration, which is feet per second squared. Okay, in our first example, we want to calculate the mass in slugs of an object whose weight at sea level is 1 pound. Okay, in our United States system, we use 32 feet per second as the acceleration due to gravity. So this is a very basic problem. We just have to put the numbers where they belong. We've got 1 pound is equal to the mass times 32 feet per second squared. Okay, so now all we have to do is divide both sides by 32. And we get the mass of this 1 pound object is 0.01325 slugs. In this next example, we're going to look at finding the center of mass in a one-dimensional system. Okay, a very common example of a one-dimensional system is when we have a seesaw and people sitting on the seesaw. Okay, if you were ever a small kid on a seesaw with a larger kid, you know that if they sit out at the end of the seesaw, that you're going to be up in the air and there's no way for you to get down again. So if you were going to seesaw with a larger child, you would need for that child to move in a little closer to the fulcrum and you move out toward the end to be able to balance. And so that's what we'll be looking at. Okay, let's look at an example. This is going to be -5, and I'm going to have a mass here of 10. And then at 0, I'm going to have a mass of 15. And then at 4, another mass of 5. And then finally at 7, I have a mass of 10. Okay, so we want to find out in this situation, where is the center of mass? Where's the point of equilibrium? If I wanted this to balance on a fulcrum, where would I have to put the fulcrum for it to balance? Okay, so for right now, we're going to assume that this system has a fulcrum at 0. And to find the moment about the origin is equal to mass number 1 times the x value of number 1 plus mass number 2 times the x value of number 2, and so on. So let's just put the numbers in. Our first mass is 10 and -5. Our second mass is 15 at 0. We've got 5 at 4. And then we've got 10 at 7. Okay, so I've got -50, 0, 20, and 70. So when I add all those together, the positive numbers are 90 minus 50 is going to give me 40. So that's my moment about the origin is 40, which means I'm going to tip this way a little bit. Okay. In this particular problem, if I add up the masses, I got 10, 15, 5, and 10. That's also 40. So the mass of the whole system is 40. Okay. And then to find the center of mass, I'm going to divide the moment by the total mass. So I'm going to have 40 divided by 40 equals 1. So the center of mass is at 1. Here's my center of mass. In this next example, we're going to look at finding the center of mass for a two-dimensional system. Okay, a seesaw is a one-dimensional system. All the masses are right along the surface of the seesaw. But now we're going to look at a problem where I've got a mass here, there's another one up here, over here, and down here. Where is the center of mass? We'll have to do two calculations for center of mass, one for the x-coordinate and one for the y-coordinate. So the moment about the y-axis, remember in the last problem, we were finding the moment, the twisting motion, around the y-axis. So that's going to be mass 1 times its x-coordinate plus mass 2 times its x-coordinate, and so on. And as you might have guessed already, my moment about the x-axis is found using y coordinates. Okay, and we want to find the center of mass. We're also going to need to know the total mass of the system. So my total mass is M1 plus M2, M3, and M4. Okay, this is the easiest calculation. Let's do this one first. I've got a mass of 6, a mass of 3, so that's 9. Another 9 is 18, and 2 is 20. So the total mass of my system is 20. And let's look now at My and Mx. For My, the mass of this point is 6 times its x-coordinate of 3. And then going to M2, we've got 3 times 0. M3 is negative 5 times 2. And then M4 is 9 times 4. So this is 18 minus 10 gives us 8, plus 36 gives us 44. Now to find the moment about the x-axis, we're going to use those same masses, but use the y-coordinates. We start again with 6, but this time it's negative 2. 3 times 0 again. And then 3 times 2. And 9 times 2. So now I have negative 12 plus 6 gives me negative 6. Plus 18 is going to give me a positive 12. So those are our moments. And to find our center of mass, we just have to divide each of these numbers by 20. So 44 divided by 20 can be reduced to 11 over 5. And 12 divided by 20 can be reduced to 3 over 5. Okay, so my center of mass for this whole system is 11 over 5, 3 over 5. I'm sure some of you are wondering, well, this is all well and good, but what's it got to do with calculus? We've only been doing basic math so far. Well, never fear, we're about to do some calculus. Okay, we're going to talk in this example about a planar lamina. And a planar lamina is basically just a flat sheet with a given area that has a constant density. Okay, so it weighs the same amount everywhere. Okay, and if we want to find the center of mass of this, we need to use a little calculus. Okay, we represent density with the Greek letter rho. So when you see that, that's the density. And so if I have a planar lamina like this area here, its mass is equal to the density times the area. Okay, looking a little closer at this picture, I can see that the height of this representative slice is f of x, and the width of that slice is delta x. So going back to what we have for calculus, the mass is equal to the density rho times the integral for f of x and g of x. If we assume f of x is larger, we're going to have f of x minus g of x dx. Okay, let's look at a couple of equations. You may want to add these to your reference booklet. So the moment about the x-axis, m sub x is equal to rho times the integral from a to b of f of x plus g of x divided by 2 times f of x minus g of x dx. Okay, the moment about the y-axis is a little bit simpler. It's just f of x minus g of x dx. Okay, if I want the center of mass, I would write that as x bar, y bar, and x bar would be moment about y divided by the total mass, and y bar would be m sub x divided by the total mass. And the total mass is described by this equation, rho times the integral from a to b of f of x minus g of x dx. Okay, so there's the equations we're going to need for this. In this example, we're going to use this equation, f of x equals 4 minus x squared, as the upper boundary of our area, and use the x-axis as the lower boundary. So our mass is going to equal rho times the integral. We went from -2 to +2. 4 minus x squared dx. Okay, so we're going to integrate now. And we get 4x minus x cubed over 3, evaluated from -2 to +2. And so this is going to be 32 rho divided by 3. That's our mass. Okay, now we're going to find the moments. The moment about x is the integral, rho times the integral from -2 to 2, 4 minus x squared over 2 times 4 minus x squared dx. Okay, when I multiply that all out, I'm going to take the 2 out here with the rho, so I have rho over 2. And so now I'm just squaring this. I get 16 minus 8 x squared plus x to the 4th dx. Come back up here and integrate. So now I have rho over 2 times 16x minus 8x cubed over 3 plus x to the 5th over 5. And we're going to evaluate from -2 to +2, which ends up giving me 256 rho divided by 15. So to find y bar, we need to take this answer, m of x, and divide it by the mass that we found earlier, which is 32 rho over 3. So I'm going to take this number and divide it by this number. I've got 256 rho over 15. And I'm just going to flip this one over and multiply. So I've got 3 over 32 rho. The rows cancel out. The 3 cancels with the 15 and leaves a 5. 256 divided by 32 gives me 8. So my answer is 8 over 5. In our last problem, we were working with a region that was symmetric about the y-axis, which simplified our work a great deal because we didn't have to find that moment since the region was symmetrical. In this problem, we're going to take the same region, but instead of using the x-axis as the other border, we're going to use this line y equals x plus 2 for our border. And of course, this is going to change up our calculations a little bit. Okay, we'll start by finding the area. Area is equal to the integral. I see here that I've got -2 for an intersection point, and the other intersection point is at 1, 3, so we're going from -2 to 1. We have 4 minus x squared minus x plus 2 dx. Okay. Simplifying this, yeah, let's do it here. I have negative x squared minus x, and then I have 4 minus 2, so plus 2 dx. Okay, when I evaluate that, I get 9 over 2. So let's just make a little note here. Area is 9 over 2. And now I want to find the centroid of x. We know we're eventually going to be dividing by that area, so we'll just put it in there now. Okay, since my area was 9 over 2, I'm going to change this to 2 over 9. And then putting this all together, I'm going to have negative x cubed minus x squared plus 2x dx. And when I integrate, I have negative x to the 4th over 4 minus x cubed over 3 plus x squared dx. Okay, when I substitute in on this one, it's evaluated from negative 2 to 1, and my result is negative 1/2. So once again, I'm going to write that up here so I have a little more room to work. X bar is negative 1/2. Now let's look at y bar. So negative 2 to 1. 4 minus x squared times, plus, not times, x plus 2 divided by 2 times 4 minus x squared minus x plus 2 dx. Okay, once again, I'm going to substitute in for a would be 2/9. I'm also going to take the 2 out here, so those cancel, and I'm going to have 1/9 there as the integral from negative 2 to 1. X squared negative x squared plus x plus 6 times negative x squared minus x plus 2 dx. Okay, when I multiply all of that out, I have 1/9 times the integral from -2 to 1 of x to the 4th minus 9x squared minus 4x plus 12 dx. And now I can integrate. I have 1/9 times x to the 5th over 5. This would be 9x cubed over 3. But I can reduce that and just make it 3x cubed. Here I would have 4x squared over 2. So I'm just going to make that 2x squared plus 12x, evaluated from -2 to 1. When I work that all out, I end up with 12 over 5. So that's my y bar, 12 over 5. So my centroid is x bar, y bar is equal to -1/2 12 over 5. Sometimes, if I have a simple plane region, I can find the centroid without having to do any integration. Let's look at this example. I've got a region here, and I've already put it on a coordinate grid and divided it up into 3 sections. Each of these sections is a rectangle, so I can find the centroid pretty easily, and then I can more or less take an average of those to find the centroid of the entire shape. Let's take a look at how that's done. Okay, I chose to put the coordinate system so that one corner of the shape was at 0, 0. That's not the only way that it could be done. If I had a symmetrical shape, it might be a good idea to put the line of symmetry right on the y-axis. Then I would only have to find the centroid in one dimension. But this is not a symmetrical shape, so that wouldn't work here. But I did look at just this little triangle, and it has a centroid of 1/2, 3/2. And it has a weight of 3. There's 3 square units there. This one is 5/2, 1/2. And it also has an area of 3 or a weight of 3. And then this last one over here has a centroid at 5, 1. And it has a weight of 4. It's a little bit bigger than the other pieces. So the area of the entire region is the 3 plus 3 plus 4, or 10. Okay? If I multiply the x coordinates by the weight, I get 1/2 times 3 plus 5/2 times 3 plus 5 times 4. And this gives me a total of 29. I take the 29, divide it by the weight of 10, and I get 2.9. And this is my x bar. I can find y bar the same way using y coordinates. So I'm going to have 3/2 times 3 plus 1/2 times 3 plus 1 times 4. This gives me a total of 10, and of course 10 divided by 10 tells me that y bar is 1. So my centroid is 2.91. So that would be right about here on this shape. Okay, our last topic in this section is the theorem of Pappus. And this theorem is another way that we might find the volume of a solid of rotation. So I've got a circle here, and I want to rotate it around the y-axis. And if I do that, I'm going to end up with a donut shape called a torus. So we're going to use the theorem of Pappus to find the volume of this torus. Just briefly, this is what the theorem says. If I have R be a region in a plane, and L is a line in the same plane such that L does not intersect the interior of R, and small r is the distance between the centroid of R and the line, then the volume V of the solid of revolution formed by revolving R about the line is V is equal to 2 pi little r times A, where A is the area of the region. Okay, 2 pi r might sound familiar. That's our formula for the circumference of a circle. So we're going to take this circle, rotate it around in a circle, and we want to find the volume of that. Okay, this circle has a radius of 1, and it's 2 units out from the y-axis. So let's see how we can use the theorem of Pappus to find this volume. Okay, the equation of our circle is x minus 2 squared plus y squared equals 1. Okay, we can see that the distance from the axis of rotation out to the centroid of the shape is 2. So that's little r is 2. Okay, the area of this circular region is equal to pi r squared. Okay, and we know the radius of this circle is just 1, so the area is just pi. Now we're going to use Pappus's equation, which is volume is equal to 2 pi RA. And this little r is not the radius of the circle, it's the radius of the rotation. Okay, so let's put in things we know. 2 pi The radius of the rotation is also 2, and we found that the area was pi units. So we get a total of 4 pi squared, which is approximately 39.5. Okay, so nice little shortcut. It does have some rather specific requirements. Again, our axis of revolution cannot be inside the area, and we have to already know the centroid. This is very nice for a circle since it was very easy to find the centroid. And that is the end of section 6.